In this video, we will be demonstrating the fundamental process for installing a Sensuron distributed sensing fiber optic cable to a substrate for the purpose of measuring distributed mechanical strain. The first two steps for any strain fiber installation involve thoroughly cleaning the surface. You want to remove any dirt, grime or grease or anything else from the surface of the structure so as not to interfere with the curing of the adhesive. And then you also want to abrade the surface such as to provide a little bit of a mechanical means for that adhesive to grip onto the surface of the structure. This makes sure that you maximize the accuracy of your strain measurements as well as maximizes the longevity or the fatigue life of the installation itself. So to do that, the Sensuron recommended way is to choose silicon carbide paper, wet dry sandpaper essentially. And you can choose the correct grit according to the material that you're using, whether it's steel, aluminum, carbon fiber, so on and so forth. And there's many online resources to help guide you through that selection processes, but there is a correct grit size depending on the material that you're using. Feel free to contact Sensuron and speak with the applications engineers to help make that selection depending on the material that you're working with. Next is, it's not required, but we like to use a sanding block. This helps you distribute the pressure that you apply as you're going through the abrasion process. This helps you avoid any non-uniformity in the abrasion pattern. So some areas are deeper than other areas. It helps distribute that pressure. It's very important when you do the abrasion to do a plus or minus 45-degree crosshatch pattern. This avoids any directionality to the installation and just helps get a more accurate and better performing strain gauge installation. So for a structure like this, it's small enough to where I'm just going to go ahead and abrade the entire surface uniformly using that crosshatch pattern. Obviously, for a much larger structure that you can't just put on a table, you would only want to do about plus or minus 1 inch on either side of where the fiber is going to be installed, and you do that all the way down the length. So this is what that looks like. Again, I'm just going to do it uniformly across the entire structure, a plus or minus 45-degree crosshatch pattern. You continue that process until you get a nice uniform density abrasion pattern. So I've got all the tools and materials needed to do so here in front of me. I'll start here with the substrate or the structure that we will be bonding the fiber to. This is a 36-inch long by 8-inch wide aluminum beam that we intend on setting up in a cantilever fashion and applying bending loads to, as well as twisting or torsional loads to. So the fiber route that we have chosen that will allow us to pick up on all of those different strain components is shown here in this engineering drawing that I'm going to be using as reference throughout the process. What we've chosen to do is install the fiber straight along this back edge. It's going to circle back straight along this front edge, and then we're going to be installing a plus or minus 45-degree sawtooth pattern which will allow us to pick up on the torsional strain. So these two straight legs will allow us to pick up on only bending components, and then the plus or minus 45-degree sawtooth pattern will have some part bending component as well as some part torsional component. We have all of the basic drafting tools necessary to lightly scribe the intended fiber route onto the surface of the beam for use as an easy reference. We have some surface preparation materials. So I have some sandpaper for abrading the surface as well as a sanding pad. I have some isopropyl alcohol for cleaning the surface and some conditioner and neutralizer for preparing the surface for an adhesive. The adhesives that we will be using, there are two of them. This one is Imbond 200 from Micro Measurements. It's a CA or cyanoacrylate glue. We will only be using this one to spot glue the fiber in place, just to hold it in place along its intended route. We could perform the entire installation with this, but Sensuron's go-to adhesive for anything kind of longer term is this 2-part room temperature cure epoxy from Micro Measurements. Both of these adhesives are from Micro Measurements. So this is the Imbond 200, and then this is the AE10 2-part epoxy. So with this adhesive, once it's held in place and spot glued, we will go in with the epoxy and apply a continuous line of adhesive as the final installation. We have some masking tape in order to mask off our glue lines. This just helps keep your glue lines nice and straight and clean, and also helps you control glue thickness a little bit better. This is not absolutely required, but it is Sensuron's recommended method. We also have some gauze pads, or you could also use lint-free wipes. This is just for cleaning the surface as well as for applying the final adhesive. Lastly, that brings us to the fiber optic sensor that we will be using. This is just a pre-spliced sensor that we prepared beforehand. So we have some length of continuous FBG fiber sensor here, which has been spliced to an FC APC patch cord that has been cut and turned into a very simple short pigtail. For instructions on how to do that splice and create the sensor, please refer to Sensuron's other instructional video, which goes over that entire process. So at a high level, what a strain installation process looks like is you will have your specimen, you will clean it thoroughly, you will then abrade it. In this case, we've done a plus or minus 45-degree pattern. Normally you just do it where the fiber is going to be installed. In this case, because we are working with such a small specimen, we just did a uniform abrasion with that plus or minus 45-degree pattern. Once that's done, we will go in and re-clean the surface just to remove any particulates caused by the sanding process. You don't want any grease or particulates on the surface of the beam when you're installing the fiber. And lastly, you will go over and apply the conditioning and neutralizing process in order to prepare this surface for the application of an adhesive. Once that's done, we will then go in and use the masking tape to mask off where the glue lines will be. Once that is done, we will then go in with the fiber and the CA glue and spot tack the fiber in place, again, just to hold it in place for the application of the final layer of adhesive, which is the two-part epoxy. So in this case, because the processes aren't unique to fiber optics, we've gone ahead and cleaned the surface, abraded the surface, re-cleaned the surface, and then applied the conditioning and neutralizing step, as well as gone in with our drafting tools and marked off or scribed very lightly the intended geometry pattern. So those first few steps are already completed. We're gonna go ahead and jump right into masking off the glue lines before we start spot tacking the fiber in place. Here I have completed the masking off process. I have taken my masking tape and taped it about 4 to 5 millimeters off of each side of the center line, or the scribe point where my fiber is actually going to be installed. So now, when we remove this tape after applying the final layer of adhesive, we will be left with nice, clean glue lines. The next couple steps, I'm going to go back over this since I've been touching it while applying the tape. I'm going to go back over it with the isopropyl alcohol, conditioner, and neutralizer, prepare the surface for the adhesives, and then we'll move on to tacking the fiber in place along this desired route. Now with the route fully masked off and the surface completely prepared, I've put on gloves to avoid introducing any additional grease or contaminants to the surface of the fiber, and I'm going to clean off the fiber to make sure it also does not have any grease or contaminants on it. First step in tacking the fiber down is to always start with the pigtail. So typically I just put a very small line of CA glue where I want the splice to be held down, hold it down, and then allow that to cure before moving on. Immediately coming out of the splice, the fiber is actually raised off of the surface. So this first, I'd say about 2 to 3 inches of fiber, you do not want to rigidly bond to the surface of this structure. You want to use the first 2 to 3 inches as a strain relief. If it's rigidly bonded, because of that gap, you can often have all sorts of stress and strain concentrations. The fiber may break, or sometimes, depending on the strain at this part of your structure, you can even pull the splice apart within the splice sleeve. So we highly recommend that the first 2 to 3 inches of fiber is left unbonded, and then you start your rigid bond from that 2 to 3 inch point onwards. To protect that first 2 to 3 inches of exposed unbonded fiber, we often go back with RTV silicone and just pot that whole area in RTV so it is well protected. So I'm going to start by tacking down the splice sleeve. Now that the splice sleeve is tacked down, the first 2 to 3 inches of this particular installation is going to be used to go around this first curve, and my first beginning point of a rigid bond will begin right here and then throughout the rest of the installation. So my first tack point is going to hold the fiber down to the surface right here. When installing these tack points, you want to use as little CA glue as possible and use a lint-free wipe or a gauze wipe to quickly wipe up any excess CA glue. The goal of the rest of the tack points is simply to hold the fiber flush against the surface. So depending on the structure that you are installing the fiber to, the frequency of your tack points will vary. The general rules of thumb is that on straight sections, we typically do about every 20 to 30 centimeters. and then at the beginning and end of any curved section or any bend in the installation. If your structures are concave or convex or other more complex structures, then you will have to use more or less tack points as necessary. But the general rule of thumb is you always want the fiber flush against the surface, because if the fiber is raised off the surface, the strain reading from that location will not be accurate. So I'm going to continue down this length and put tack points as necessary just to hold the fiber in place, flush against the surface of this aluminum beam. It's also important to note that when doing these straight sections and putting these tack sections down or tack points down, you do not want to induce significant tension between individual segments of tacks. So whenever I'm holding this segment of the fiber down, I'm being careful not to pull it, because these regions of the tack points, if you do put tension on each of these segments of fiber between the tack points, it can result in some localized high noise points in the output of the Sensuron devices or Sensuron interrogators. So as I'm going through this process, I'm being very, very careful not to induce significant tension before I put a tack point down. So now I have my entire fiber sensor initially tacked down, and I'm going to actually go back over it and check that the whole thing is sitting flush against the surface of the beam. If there's any point that's resting above the surface, I will just add another tack point between the two that are already there. The way that I go through and check this is I just go through between each set of tack points. I just lightly tap the fiber with your gloves on so you don't introduce any grease. Just lightly tap the fiber, and if you see any vertical movement, then you know you should add a tack point between the two existing tacks. So I'm going to go ahead and do that through all these different tacked sections, and then reapply any additional tacks as necessary if there is any fiber lift from the surface. So here the fiber is completely tacked down everywhere along its length. I've made sure that there is no fiber lifting from any part of the surface along the entire installation route. I have my epoxy mixed, it's ready to be applied. So what I'm going to do next is I will take the epoxy, I'm going to pour a little bit all the way along the fiber, all the way along its entire installation route. And then I'm going to take a piece of closed cell foam, closed cell so it doesn't absorb a bunch of epoxy, and I'm going to smear out the epoxy such that it spreads out all the way out to the masking tape. I want it all the way out along the masking tape, all the way along so it's nice and evenly spread on both sides of the fiber, everywhere along the length. Once that's done, I'm going to wrap this piece of foam in some gauze and start re-wiping it in order to remove all of the excess epoxy. What we're ultimately looking for is kind of a uniform application of epoxy all the way out to the masking tape. And then I want to have as little epoxy as possible, such as only to leave a small fillet on either side of the fiber and just a small amount going over the top of the fiber. So we'll go ahead and get started doing that. Starting at the very first tack point, avoiding the unbonded portion that I'm using as a strain relief. And just pouring it along the entire installation route. I'm going to take my closed cell foam. Get it started, spread all the way out to the edge of the masking tape, and then just kind of nice and continuously go along the entire installation route. This initial smear is simply to spread it out to the masking tape, and then I'll start the removal process. A little bit more glue for this section. Now that the glue is initially smeared out, I'm going to wrap this in gauze and start removing as much of the glue as I can. Leaving just enough to create a small fillet on either side of the fiber. Depending on how much epoxy you use initially, you may have to go over this once, twice, a few times to get the right amount uniformly distributed across the entire length. So at this point, I'm going to let the adhesive start to set up, which will take anywhere from about 15 to 20 minutes. But before it's fully cured, I'm going to come back and start removing all of the masking tape and then allow it to fully cure for at least 24 hours. It's been about 15 minutes since I removed the excess epoxy. So at this point, I'm simply going to remove the masking tape, and then we will allow this beam to cure at least for 24 hours for this particular epoxy, or you can leave it for however long your particular adhesive requires to cure. At this stage, the epoxy has fully cured, and now we can give a better close-up view to some of the features of the installation. So here is where our splice and our pigtail were bonded to the structure. The fiber comes out of the splice, and the first 2 to 3 inches is not bonded down to the structure. Again, this is just to provide a simple strain relief, and we will be going back and potting this entire area within some RTV silicone or some tank sealant to provide a layer of protection. And then from then on is when the fiber is rigidly bonded to the structure for strain transfer. Again, just using enough 2-part epoxy to create a very small fillet on either side of the fiber. Another option at this point is you can go back over the entire installation with a layer of tank sealant or RTV silicone just for an extra layer of protection. So if you drop tools or anything else on, say, an aircraft wing or some structure that people are crawling all over, disassembling, reassembling, it minimizes the risk of fiber breakage. At this point, we have allowed the epoxy to fully cure, and the installation is now considered complete. So we can now take this sensor, connect it to the Sensuron interrogator, to any of our interrogators, and validate that we are getting the strain distributions that we expect given how we have set the beam up, the fiber routing, and the loads that we apply. So I've hooked it up to a Sensuron RTS 125 Plus system, and that leads to the lead length or the offset length, to the broadband reflector, to the sensor pigtail, which leads up to the sensing fiber on the surface of the beam here. I've taken the beam and connected it in a cantilever fashion to this I-beam, so it's anchored at its base over here. And then of course we have a freestanding end extending out this way. So I'm going to be applying a tip deflection as well as torsional loads at the freestanding end. So given the fiber routing and how we have it set up, what we expect to see is a linear bending strain distribution coming from the first 2/3 of the fiber, which are these straight segments. These segments should also have no torsional component. And then for the last third, the zigzag segment here, it'll have a smaller magnitude bending component compared to these straight sections. And it should also have a very clear torsional component of strain. So the output over here is shown. It's a simple XY plot, and the X-axis represents the length along the fiber, starting at where the installation starts here, and then just running as a function of arc length along the sensor all the way out to the end of the sensor over here. The Y-axis is of course strain in terms of microstrain. So I'm going to start with just a bending load. I'm going to deflect the tip of the beam downwards, and you can see that we do in fact get the expected strain distributions. So the first 2/3 of the output between sensors 502 and 802 represent this section of the fiber where it's straight down the trailing edge, circles back, and returns straight again down the leading edge. So this is a nice linear distribution from this tip load as expected, with the maximum values down here at the base, and then running to 0 down here at the tip. The zigzag portion, of course, does have a bending component, which we can see in the last third. However, it is smaller in magnitude because of the off-axis nature of the installation. With a downward tip deflection, the top surface is placed into tension, which we can see here as positive strain, as expected. We can also deflect the tip upwards and see essentially the same distribution, but now in compression. We can also apply a torsional load. We can see that for the first 2/3 of the installation, for the straight portions, the component is 0, it does not see any torsional strain, but the zigzag portion has a clear indication of the torsional load. It sees alternating tension and compression depending on the direction of twist that I am applying. And then of course, we can see coupled loading, so both bending and twisting. So this measurement very clearly indicates how loads from bending and twist are distributed throughout the length of this beam. Another application using this data could be to take the strain information, decouple the bending components from the torsional components, and utilize those measurements to calculate the continuous deflection shape and also twist shape, so the overall shape of this beam as it's being deformed.